This is Nernst, the neuron. He's dedicated to teaching you all about the brain. Today, we'll be learning about the neuron and its resting membrane potential.
Imagine a vast city. This is our neuron. Its imposing walls are constructed from tightly packed phospholipids, a double layer of molecules to ensure protection and to limit entry of most substances. These walls are waterproof, an impenetrable barrier to most travelers. However, they are not completely secure. Gates or ion channels are found at points along the wall. Each gate operates according to its own rules. Some gates, like the potassium gates, only allow townspeople, or potassium ions, to join. Other gates, like sodium gates, permit entry to visitors, sodium ions. There are gates that are locked most of the time, but may open based on a change in voltage in the city. These are the voltage-gated channels. There are also gates that will only open when a special messenger brings a key to allow entry into the city. These are the ligand-gated channels. Meanwhile, the hard-working guards with wagons, the ion pumps, are constantly at work. The most famous one, the sodium-potassium pump, trades 3 sodium ions out for 2 potassium ions in, burning ATP for every trip. Over time, this creates an uneven distribution. Inside the city, there are far more townspeople, or potassium ions. Outside, the countryside is filled with visitors, the sodium ions, and nobles, the calcium ions. This imbalance is the foundation of electrical potential. Like a charged battery, the inside of the city becomes slightly negative compared to the outside, at about negative 65 millivolts. This is the resting membrane potential, that hum of readiness that allows neurons to fire. You can picture the city's border as an invisible tug of war. The townspeople or the potassium ions want to wander out. There are too many of them inside. But as they leave, they make the city more negatively charged, pulling their friends back in. Eventually, a balance is struck between 2 opposing forces, diffusion, pushing potassium ions out along its concentration gradient, and electrostatic attraction, pulling it back toward the negative city interior. That point of perfect balance can actually be described mathematically by the Nernst equation. This is an equation that predicts the voltage at which one specific ion's desire to move stops. Think of it as the city's mathematical peace treaty. This is the exact point where the urge of the townspeople to leave is perfectly balanced by the electrical pull drawing them home. The Nernst equation compares 2 forces. Number 1, the concentration gradient, how many more potassium citizens there are inside than outside, for example, and the electrical gradient, the charge difference that builds up as they move. For potassium, this equilibrium potential, EK, is about negative 80 millivolts. If the city's charge matched that exactly, no potassium would move at all. But our city's potential is negative 65 millivolts, not negative 80. Why? Because the walls aren't only open to potassium. A few sodium gates leak, allowing the sodium ions to slip in, slightly offsetting the balance. To describe this more realistic situation, where multiple ions contribute based on how open their gates are, scientists can use the Goldman equation. It's like the city council calculating the overall tension across the wall by considering how many gates each group has, or permeability, and how unequal their numbers are inside versus outside, or the concentration gradients. Using the equation, we see that, number 1, if potassium gates are the majority, the city leans towards EK of negative 80 millivolts. But number 2, if sodium gates open wider, the potential shifts towards ENA, or 62 millivolts. At rest, the city's permeability is about 40 times higher for potassium ions than for sodium, so the final vote, or resting membrane potential, lands closer to potassium's preference, around negative 65 millivolts. The Goldman equation shows more this democracy, as it shows the balance of all ionic citizens contributing to one stable electrical tension. But when the call comes, when voltage-gated sodium channels open, the peace ends. Crowds of sodium ions flood in and flip the city's charge from negative to positive in milliseconds. This wave of electrical change travels down the city's highways, or the axon, carrying the signal that lets us think, move, and feel. Soon, the pumps are able to restore order by pushing the ions back to their sides to rebuild the imbalance and reset the city's voltage. Once again, the neuron rests, charged, ready, and waiting for the next signal.